So here, let's look at an action potential. Now, an action potential is demonstrated by some rapid changes in that resting membrane potential, and it involves opening and closing of different types of channels. All right, we call them voltage-gated channels, and it specifically voltage-gated sodium and potassium channels. All right, so let's talk about how an action potential works, and we'll use this graph that you see in the video to guide us. All right, this graph is going to show us the changes in that cell membrane's potential over a period of time. Okay, you can see from its resting state to an action potential and then back again. On the x-axis here, you'll see time in milliseconds, and then on the y-axis is going to show you what that membrane potential is, and it's measured in millivolts. All right, so first let's look at the timeline, which is going to span about 5 milliseconds. At 0 milliseconds, the cell is at its resting membrane potential, and you can see that's going to be about negative 70 millivolts for neuron. This is going to be the baseline voltage when the cell is not active. Okay. As we move forward in time, we can see 5 stages of the action potential. We see the resting state, the stimulus and the threshold, depolarization, then repolarization, then hyperpolarization, before it finally returns to the resting state again at around about 5 milliseconds. And we'll break this down by step here. So again, we're looking at the resting membrane potential, and at rest, the inside of the cell is more negative compared to the outside. It's going to be around negative 70 millivolts. All right, this is going to be maintained by potassium leak channels, right? This is where we have potassium ions that are allowed to slowly kind of leak out of the cell. It's also going to be maintained by that sodium-potassium pump, which we have 3 sodium and 2 potassium ions moving to keep that ion gradient stable, as well as we have voltage-gated sodium and potassium channels. Okay, and at this point, those are closed. Okay. At time 0, this is where we have a stimulus. That stimulus is going to cause a slight increase in the membrane potential. It moves it closer to the threshold, around about negative 55 millivolts. Now, if that stimulus is strong enough to reach the threshold, it's going to trigger the opening of those voltage-gated sodium channels. All right, and that's going to start the action potential. All right, then what we have is what's called depolarization. This is going to be the time between about 1 and 2 milliseconds, and we're going to see that sharp rise on the graph. Okay, we're calling this depolarization, and this is where the inside of the cell is going to become less negative, and it even turns positive for a period of time, and it's going to reach about positive 40 millivolts. All right, though the reason this is happening is because those voltage-gated sodium channels are fully open. All right, they're going to allow sodium ions to rush into the cell. That sodium influx is what's driving this depolarization phase. At around 2 milliseconds, the graph you can see will start to drop back down. All right, this is what we call repolarization, where the cell returns to that negative membrane potential. All right, what's happening here is we have voltage-gated sodium channels will be closing. All right. Voltage-gated potassium channels are open, and it allows potassium to flow into the cell. This outflow of it allows potassium ions to flow out of the cell. Now, this outflow of positive potassium ions is going to allow that membrane potential to be brought back to that resting state. Okay, and then you see between 3 and 4 seconds, we have the graph dip, and it goes below that resting potential. Okay, we call this hyperpolarization. And this is occurring because those voltage-gated potassium channels are going to stay open a little bit too long. All right, and they do that to allow extra potassium ions to leave the cell. And that's going to make the inside of the cell even more negative than usual. All right, it'll go to about negative 80 millivolts. All right, there's a reason for that. It's advantageous. And we'll learn about that soon. Then we're going to return to that resting state by about 5 milliseconds. Okay, the graph stabilizes back, and we're back to negative 70 millivolts. And this is happening as voltage-gated potassium channels are closing. All right, and then those sodium-potassium pump that sodium potassium pump is going to restore that original ion concentration that we had at the very beginning, right before the stimulus. All right, and this is going to prepare the cell for the next action potential. All right, so let's connect the curve to the ion movements that are driving it. During depolarization, all right, here we have sodium ions rushing into the cell. They make the inside more positive. Then during repolarization, potassium ions flow out of the cell, and that restores the negative membrane potential. During the hyperpolarization phase, there's a prolonged outflow of potassium that makes the cell even more negative. All right, so why is this important? Real life. Okay, well, this process is vital for many different body functions. Let's look at a neuron. Action potentials will allow the brain to send signals to your muscles or organs. Now, in the muscles, they're going to trigger contractions, kind of like your heartbeats when you move your arms. Okay, disruption in this process, such as problems with sodium or even potassium channels, will lead to medical conditions like seizures or paralysis or even cardiac arrhythmias. All right, now this graph and the action potential it represents are really the foundation of how our nervous and muscular systems work, as well as some cardiology too. So by understanding the roles of the sodium and the potassium and how they move through specific channels, we're able to see how these electrical signals in the body are generated and controlled. A recommendation that I would make is that you print out this image and you write what ions are flowing at each different stage, what channels are open, what channels are closed. All right, that would be a very good learning tool for you to have on your study guide.